Hi folks, we're now going to look at the surface area for a solid of revolution. We'll start by reviewing how we determine the volume for a solid of revolution. So we'll take a look at this diagram here and remind ourselves that we took some portion of a function, say defined from A to B, and then we revolved it about an axis. In this case here, I've revolved it about the x-axis. Since this is a solid of revolution, all the cross sections will be circles. So we use disks in order to estimate the volume of the solid. So in any subinterval of our partition, we pick a CI, and the function value at that CI acts as our radius for our disk. We can find the volume of this disk, set up a Riemann sum, and as long as the function inside the Riemann sum is continuous, we can then integrate to find the true volume. Now this worked well when we were trying to model the interior of this solid, but when we're trying to determine the surface area, it's only the exterior that we're interested in modeling, and so we need something that models the shape of the curve. Now unless you're at a flat part of the curve, a horizontal line won't be a good model for the shape of this curve, as we can see in this little part in this partition here. Even if we made this partition smaller and smaller, a horizontal line just won't cut it to estimate the shape of this curve. So we need another way to do this. Now some of you may have already been thinking about using not these horizontal lines, but like we did with the length of a curve, the secant joining the two endpoints of the subinterval, and that's what we'll look at here. So we do exactly that. We consider our same subinterval, and we consider the secant joining the endpoints, and this is a good model for the shape of the curve, and it gets better and better as these subintervals get smaller and smaller. So what we now have to do is determine the area for this exterior shape. The question is, what is this exterior shape? It's no longer a cylinder. So we're now going to take these lines and actually just extend them. And as we extend them, we realize that this surface here is just the bottom portion of a cone. Now you may remember from grade 9 solving problems involving portions of a cone, either finding the surface area or finding the volume of these things here. And in fact, this shape is called a frustum. Not necessary to know the term, but I guess for your own cultural knowledge, this part here is called the frustum of the cone. So our first goal is going to be determining a formula for the frustum of a cone that then we can hopefully use to create a Riemann sum, and again use integration as a way to determine the surface area. We'll take a look at that in part 2 of surface area of a solid of revolution.